Alright, in this video we're going to take a look at the standard reduction potentials chart, which is in your data booklet, and just see some things that we can actually learn from looking at this table. So it's called a reduction potentials chart. If you look at each of the chemical reactions on the chart, you'll see that something is gaining electrons, and of course gaining electrons is a reduction process. So these reactions are all written as reduction reactions. Fluorine gains electrons and makes fluoride ions. Gold 3 plus gains 3 electrons and becomes gold metal, which is neutral gold. So each of the reactions is written as a reduction reaction. The numbers on the side have the symbol E with a degree symbol, or E naught, and their units are volts. So these are the standard reduction potentials for each reaction. Standard, that's what the degree symbol means, beside the symbol E, refers to the fact that if there's anything aqueous, its concentration is 1 molar, the temperature is 25 degrees Celsius, and if there's any gases in here, the pressure would be standard pressure, 101.3 kPa, or 1 atmosphere pressure. Now you remember, when looking at this chart, in the middle of the chart is the hydrogen ion being reduced. So hydrogen ions gain electrons to make hydrogen gas, and that is given a voltage of 0 volts. And that's an arbitrary decision. We made the hydrogen half cell the standard against which the others are compared. So it's called the standard hydrogen electrode, and it's arbitrarily given a voltage of 0 volts. So what does it mean if something is positive potential, standard reduction potential, or if something's a negative reduction potential? The positive potentials simply mean that these substances have a greater potential for reduction than hydrogen ions. The negative potentials simply mean that these substances have lower potential for reduction than hydrogen ions. They're all compared to hydrogen, which therefore has 0 volts in the middle of the table. So don't think that a positive potential means you can be reduced and a negative potential means you won't. That's not true. The bigger your potential is, the greater is your likelihood to gain electrons. The greater is your potential, if you like, to be reduced. The lower the number is, the less likely these substances would be reduced. Now keep in mind, only the substances on the left are being reduced. If you looked at the equation backwards, you could say fluoride ions, in reading it backwards, become oxidized and lose 2 electrons to make fluorine gas. You could say silver metal, reading it backwards, becomes silver ions and loses 1 electron. So the reverse reactions are oxidation reactions. These numbers on the side would change their sign if you were looking at the reverse reaction. So in other words, if you say copper 2 plus gets reduced to make copper metal, positive 0.34 volts would be its reduction potential. We would say E naught reduction is positive 0.34 volts for copper 2 plus to become copper metal. On the other hand, if you wanted to read that backwards and say copper metal gets oxidized to become copper 2 plus and in the process loses 2 electrons, so just read it backwards, then this number changes its sign, and we would now say the oxidation potential for copper metal, the substance being oxidized, is negative 0.34 volts. Okay, so the first is the reduction potential for copper 2 plus cations to become copper. The second number is the oxidation potential, negative 0.34 volts, is the oxidation potential for copper to become copper 2 plus and in the process be oxidized. Okay? So you can get both oxidation and reduction potentials by looking at this chart. You'll remember some basic vocabulary that a substance being reduced is an oxidizing agent. So everything on the left are oxidizing agents. Things that get oxidized are reducing agents. So everything on the right-hand side, when you read the reaction backwards, those things are reducing agents. Okay, so notice the titles at the top there. The greater your potential, the greater your likelihood to be reduced. So therefore, the substances here that are highest up on the chart, fluorine, for example, is the very highest, would be the strongest oxidizing agent. On the other hand, things that are on the bottom right-hand side, lithium is at the very bottom right, lithium's oxidation potential would be positive 3.05 volts. So lithium would have the greatest oxidation potential on this chart, so lithium would be the most likely to be oxidized, so lithium would be the strongest reducing agent. Now there's some arrows on the side of the chart to remind you of that. An arrow pointing up on this side, increasing oxidizing ability. So these guys are the best oxidizing agents on the chart. These guys are the weakest oxidizing agents on the chart. On the other side of the chart, there's an arrow pointing down, okay, an arrow pointing downwards. And it says there, increasing reducing ability. So therefore, the guys on the bottom here, on the right-hand side, are your strongest reducing agents. The ones at the top here on the right-hand side are your weakest reducing agents. Now, what can you do with this chart? Well, you know from earlier in our notes that we can actually calculate cell potential for batteries, for electrochemical cells, if you have this chart. But you can also do some other things with it. For example, you might ask, suppose you were to take a piece of zinc metal and you were to dip it into a solution of silver nitrate. And you want to know, will this reaction occur? Okay, is this going to be a spontaneous reaction? Well, to figure that out, let's backtrack for a minute. Zinc metal is right here, Zn solid. Now I know from experience that zinc metal will react with acid. If I put it in acid, it dissolves and you get hydrogen gas produced. The hydrogen gas is coming from hydrogen ions being reduced. And the zinc metal, as it reacts, dissolves and produces zinc 2+. So this reaction between zinc and hydrogen ions in the acid, I know from everyday experience, is a spontaneous process. Now you can look at that and say, well, if hydrogen ions are being reduced, its potential is 0 volts. If zinc is being oxidized, its potential would be positive 0.76 volts, reversing the sign of this. And combining those two numbers, positive 0.76 and 0, you can see you get a positive cell potential, positive 0.76 volts overall. In fact, that explains why that reaction between zinc and hydrogen ions is spontaneous. When you get a positive cell potential, you have a very large equilibrium constant for the reaction. A negative cell potential would have a very tiny equilibrium constant, and the reaction essentially doesn't happen to any reasonable extent. You just say it really doesn't happen. Okay? Now, rather than calculate the cell potential all the time to see if it's positive or negative, we can just use this pattern. If you see anything on the chart where something on the left, like hydrogen ions, is reacting with something on the right and below it, like zinc in this case, you can be assured that you'll always get a positive overall cell potential. So reactions on something on the left reacting with something on the right below it will always have a large equilibrium constant. That reaction will be spontaneous. So coming back down here, will zinc metal react with silver nitrate? Well, if it does, let's just pretend it does, it'll be a single replacement reaction. You'd get zinc nitrate as a product, and you'd get silver metal as the other product. So if this were to happen, the zinc, which starts at 0, would become zinc 2 positive. The silver, which starts at +1, would become silver 0. So let's see if that reaction actually would happen. Zinc to become zinc 2 positive, well, that's this reaction again, backwards. Okay, so zinc metal is reacting, and it's reacting with silver ions. The nitrate is just a spectator. So we're asking, does zinc react with silver +1? Well, silver +1 is up here. And sure enough, it can gain electrons and make silver metal. And we notice that the connection between zinc and silver ions is that same basic connection we saw earlier. Something on the left is reacting with something on the right and below it. So on this chart, that means that reaction would have a positive cell potential and therefore would have a very large equilibrium constant. You can calculate it if you like. Silver to become silver metal would have a positive 0.80 volt potential. zinc to become zinc 2 plus would have a positive 0.76 volt potential, reversing it, and positive 0.76 and positive 0.8 will give me positive 1.56 volts. So again, something on the left reacts with something on the right below it, or something on the right reacts with something on the left above it. That basic pattern means, yes, this reaction would be spontaneous. It would happen, have a very large Kc. On the other hand, suppose you were to take silver metal, which is right here, Ag, and dip a piece of silver metal into a solution of zinc nitrate. So zinc 2 plus from the zinc nitrate is down here. Would you expect silver metal to react with zinc 2 positive? I realized my chart was off there, sorry. Silver up here on the right reacting with zinc 2 plus down here. You notice that the pattern produced is the opposite. It's something on the right reacting with something below and to the left. That reaction should be non-spontaneous. It should have a negative cell potential and therefore would not happen. You can see that that reaction is just the reverse of this reaction. If the forward reaction is spontaneous, has a very large Kc, then the reverse reaction is non-spontaneous. It'll have a very small Kc. So putting zinc into silver nitrate, yes, you would see a reaction happen. Putting silver into zinc nitrate, you probably wouldn't see anything happen because the reaction has an infinitesimally small Kc value. Okay? Very, very few products would be produced. All right, so there's using the chart to predict whether a reaction would happen. You might also be asked to rank which is the strongest or weakest oxidizing agent, which is the strongest or weakest reducing agent. To do that, you simply make sure you're looking at oxidizing agents, and you remember the strongest are at the top and the weakest are at the bottom. The strongest or weakest reducing agents, be sure you're looking at something that is a reducing agent to begin with, and the strongest reducing agents are near the bottom, the weakest reducing agents are near the top on that side there. All right, so that's some ways to use this reduction potentials chart to answer some questions qualitatively rather than quantitatively.